Hi and Assalamualaikum everyone, and welcome to our presentation. First of all, let me start by saying a few words about my own background. My name is Dani Al-Aziz and I am a group leader for this group, which is a group G. We are a group of 5 students, who is me myself, Aiman Azif, Ahmad Darwis, Kavines and Chu Jingsun. In test allocation, Aiman and Darwis will take over the ANSYS solution. However, for the geometry and simulation, we will let our group members, who is Chu, to demonstrate about it. And last but not least, Kavinas will make clear about the result and explanation. As we know, boundary layer in fluid mechanics is a thin layer of a flowing gas or liquid in contact with a surface, such as that of an airplane wing or of the inside of a pipe. The fluid in the boundary layer is subjected to the shearing forces. A range of velocities exists across the boundary layer from a maximum to 0. Provided the fluid is in contact with the surface, boundary layers are thinner at the leading edge of an aircraft wing and thicker toward the tailing edge. The flow in such a boundary layer is generally laminar at the leading or upstream portions and turbulent in the trailing or downstream portion. The objective is to obtain heat transfer coefficient and boundary layer thickness for both hydrodynamic and thermal boundaries for flow over an isothermal flat plate by using ANSYS fluent.
For the geometry detail and dimension, first we select the rectangular at top box and draw a rectangular. Next, we need to give in the dimension of the rectangular. The value of the rectangular is 1000 mm. After that, we select the height of the rectangular and set the height with 300 mm. And we recenter the view to have a full view of geometry. For the method, first we create the mesh and then we change the physics preference to the CFD. After that, we need to change the element order from the linear to quadratic. And then we need to open the automatic method. In automatic method, we need to select the rectangular and then we set the geometry. We apply the rectangular as the geometry section. And then we go to SIG. For SIG, we need to change the type to number of division. And then we set the number of division to 1000. After this, we will go to inflection. In inflection, we will select the whole geometry as the geometry section. And then we need to select the boundary of the geometry. We will use the bottom of the geometry as the boundary. Okay. We create the boundary and then create the bottom of the geometry and apply it. After select the boundary, we will change the inflection option to first layer thickness. And then we set the first layer height with 0.1 mm and maximum layers are 60 layers. Lastly, we set the growth rate with 1.1. Next, we go to body sizing. We select the geometry section for whole geometry, apply it, and then we will set the type to sphere of influence. Sphere center, we will select the global coordinate system, and we will set the radius of the sphere to 30 mm. The element size is 0.3 mm, and that we will merge the geometry. After merging, we can see the geometry turning irregular shape, and that we can zoom in the geometry to see the elements. We also can show the part of name section by click the inlet, flat plane, outlet, and symmetry.
Thank you, Teaching Sir. Now, for the method, first we will select symmetry 1 for its location, and for variable we will choose velocity. For the range, we will be changing from global to user specified. For minimum value, we stick to 0, 0 as our origin, and for the max, we can choose a certain point, specific point. For example, in this case 0.1 ms magnifying. For the number of contours, we can choose up to 11, and later we can choose to default legend view so that our view of the velocity contour will be much clearer. Next, we select the details of trailing edge, and under the trailing edge we can see the definition box. We select 2 points in the method, and for point 1 we stick at 1, 0 and 0, while for point 2 we change the middle point from 1 to 0.05 and then 0. For line type, we have selected our samples to 1000 and then we apply. In the value, we can add up to 0.0999 ms negative point. We can obtain a clearer image of the velocity isosurface. We select the box of velocity contour under the region user locations and plots. Moving on, under the details of chart 1, we change the variable of the x-axis from chart count to temperature. And then for y-axis, we change the variable pressure to variable y. And then we apply. After applying, we can see the result in the graph under the title, where we move to x-axis and we select invert axis and then we press apply. The reason we do invert axis is to obtain a proper graph and a proper result. If we click line display, we can see series 1 in bracket trailing edge. And as we scroll down, go to the symbols. Under the symbols, you can see fill area, where we click always on for fill area instead of automatic. And then we apply to obtain the shaded region under the graph.